One, two. Thank you. Okay, so we are going to start this last session, which is dedicated to machine learning, a part of AI. AI has always been very close to robotics. I don't know if it is politically correct to say that robotics is born with AI. But what happened is that in the last 5 years, we have seen very important advances in machine learning techniques, which has a big impact on robotics. So this session is dedicated to several illustrations of those impact. We will start with a presentation about pose estimation. From tactile-based self-supervised pose estimation for robust grasping. And the presentation is going to be given by Padmaja Kulkarni. Sorry. Okay. So yeah, you have to share your presentation. We see. Okay, that's perfect.
Awesome.
So you have 12 minutes plus a few minutes for the questions. Okay.
So thank you for the chance of letting me present in this conference. Today I'll talk about the paper that I wrote with Jens Kober and Robert Babushka from TU Delft about tactile-based self-supervised pose estimation for robust grasping. So general camera-based grasping approach, we first predict the pose of the object using camera and then compute grasp parameters, which could be force of position of the hand with respect to object or hand angles and so on. But grasping in the dynamic environment with this approach is quite challenging, especially when low lighting, occlusions, or shadows are present. And these challenges arise due to first incorrect pose estimation of the object. Then there could be slippage due to additional forces acting on the object while the robot is trying to move the object. And as seen in this video, the object moves while robot is attempting to grasp the object. So along with this camera-based approach, the state-of-the-art approaches use tactile sensing generally to facilitate the grasping. So this facilitation is done by generally predicting grasp stability or detecting the slip and estimating object properties and shapes so that better grasping points can be figured out, or even classifying the object and classifying the surface, for example, if the surface is rough or not, and then adjusting the grasp force accordingly. So some of the examples in this area is Calendra et al., which give, so the diagram is shown here, and they send RGB images along with the images from gel site sensors to a deep neural network, and then the neural network predicts if the grasp will be successful or not. This is useful before robot is trying to pick up the object and manipulate it. Second example, Chevitor et al., they propose a two-step approach. So the first part just predicts if the grasp is stable or not. And second part is a reinforcement learning algorithm, which is trying to configure the robot hand if the grasp is not stable, and then adjusting its input according to the supervised output from the first part. However, these approaches add little insight into the pose of the object after robot-object interaction happens, as seen in the first video. If the robot does not know a reliable object pose after the robot finger contact happens, then robot cannot precisely place the object. And it can happen that if the robot fails, then there is no way to regrasp if another input from camera cannot be possible, for example, due to occlusion. Knowing this in-hand object pose, it helps to place object precisely after picking up or regrasp if the object fails. So we formulate our problem statement as estimating the object pose during a grasp attempt, especially when visual feedback is not possible during or after the grasp. So object pose estimation with tactile sensors is not new to this area. There are certain examples from Bembo et al., Corcaran et al., and Class et al. But all these approaches, they predict object pose with certain assumptions such that object is fixed at certain point, or object model is known, or object geometrical information is precisely known. And these approaches cannot consider if there is size variation in the object or even surface property variation. In contrast, we develop a data-driven method, and we estimate object pose based on the tactile data without making any assumptions about the model of the object, grasp stability, or without fixing the object at a location. And moreover, when we are collecting the training data, we use a camera to estimate ground truth object pose, and thereby we generate the labels of the target object pose automatically in a self-supervised manner. So no human intervention is required for the labeling there. So our approach is quite simple. It is divided into 3 parts. First is data collection, where we are recording true object pose, tactile data, and finger joint angles of the robot. Then there is model training phase, where we get the collected data and we train a machine learning model to estimate pose of the object, pose of the object. And however, we process this input features in a suitable way so that the accuracy of the machine learning algorithm is better. And third is then pose estimate, where based on the single time frame tactile data, finger joint angles, and initial object pose, we predict the current position of the object. This is the setup that we used for our experiments. We use a shrunk SDH hand, and we use 2 fingers of this hand for the grasping. We use Asus Axion Pro camera to track the marker positions on the object continuously during a grasp attempt. And during evaluation, while predicting pose, we are not using any labels from the camera. Data collection algorithm is also quite simple and straightforward. When we start self-supervised data collection, we compute the initial pose using the camera, and then we move robot fingers to grasp the object. If the grasp contact detect, then we start recording the tactile readings, object pose, that is true object pose, and robot joint angles. And when the grasp attempt is finished, we stop the recording. So here, grasp attempt finished does not necessarily mean the grasp is successful. So we use our algorithm in 2 ways. If the robot has successfully grasped the object, then our algorithm can be used to detect the pose of the in-hand object pose. And if the robot has failed in grasping, then our algorithm can predict where the object has landed from the robot hand, so the robot can re-grasp the object later. Then collected data hints is the object pose for joint angles and tactile data from 2 fingertips of the shrunk SDH hand. So SDH hand has WISE tactile sensor, which consists of 6x14 array of taxels. So for example, when there is a pressure point here, then you get a distribution of taxel pressure points like this. Since the data is high dimensional, we process the data in 3 different ways. First, we just use tactile data as a list without processing anything. Then we use a max pooling operation on tactile data. So max pooling is generally used in convolutional neural networks to downsample the image data. And it essentially consists of a filter that goes over a matrix, and in max pooling, maximum of this filter value is then considered, and it becomes part of the output. So that was one of the feature processing, pre-processing step that we used. And second one was principal component analysis. Since we assume that not all 156 features are useful, so we check the covariance of the tactile data vectors, and
it was actually the training for one was finished for the training, not finished, and the person.
Sorry?
The professor was using the something like
sorry, I couldn't hear it. Was it for me?
Can you hear?
I hear a lot of echo, but yeah.
Okay.
Should I proceed with the presentation?
Yes, yes.
Okay, awesome. Then we also use principal component analysis to pre-process the data. And what we do basically is we take data corresponding to first 80% of the eigenvectors, which explain the data in a better manner. For experimentation hardware, we already discussed. Object used were a coffee box and a ceramic cup, and we collect 80 successful and unsuccessful grasp data at each time frame. And for evaluation, we use the objects that we used for training, and additionally, we cover these objects with a foam layer. So A, we change the size of the object, and B, we change the surface properties of the object. So the robot-object interaction is also quite different. And we use 4 machine learning algorithms with parameters shown in the table to evaluate. So for this presentation, I'm not going into details of the evaluation, but I can just summarize the results, that the main takeaways from it. So in our evaluation, random forest method worked the best, and all feature representation worked equally well. One of the reasons could be is because we are using only 2 fingers. But the plan is to, when plan is to use all the fingers, then either PCA or the max pool operation has a high chance of success. When the robot grasp was successful, then the error in translation was less than 0.5 centimeter and 3 degrees in rotation. And these values are enough for our robot to regrasp or to put the object precisely at the the placing location. And when grasp was unsuccessful, that is, object has slipped from the robot hand, which is generally more than 10 centimeter farther from the original position, our algorithm can detect it up to 2 centimeter in translation and 8 degrees in rotation. So it's a little bit more than we desired, but it is still sufficient for robot to regrasp the object. And then when grasping is successful, it can accurately predict the object pose for precise placement. And when the object properties and sizes changed, then RMSE was about the same as when the grasp was unsuccessful. So further training with varying object properties is required to make the method robust against object property variation and to reduce the error further. So to conclude, we proposed a self-supervised method for robust grasping tasks using tactile feedback. And our approach does not require any prior object knowledge, and it does not make any assumption about the grasp stability or even the assumption that the object is fixed and does not move under because of the robot-object interaction. And we evaluated here effect of various feature representation and machine learning algorithms and changing properties. And we found out that random forest works the best here. And result we already discussed. And in the future, we plan to evaluate the complete manipulation pick and place pipeline with more day-to-day object of irregular shapes, like lettuces, tomatoes, and chicken pieces, and with varying sizes as well. So, thank you. Yeah, sorry.
Can you hear me? Yes.
Yes, I can.
Yes, thanks for a nice presentation. I just wanted to ask, do you have a baseline that's based just on the camera instead of the tactile? Because somehow in the beginning of the motivation, you said, we don't want to use the cameras because we might not see partial observability. But then for getting the labels, you actually use the camera. So I was just wondering, so how useful is the tactile information with respect to like maybe a gripper camera?
Yeah. So labels are used only for evaluating the method, for example. And when the object actually slips or when the grasp is unsuccessful, the object moves around 8 centimeters from the original location. And when we are evaluating this, the camera position is only used to check if our prediction is close to the true value. So this 8 centimeter motion is not recorded in the camera or not used in the training algorithm. Was that clear? Sorry.
Yeah, thanks.
Thanks.
I have a question.
Hi, Padmaja. Thank you for the presentation. I just had a quick question on the feature vector that you used. So you said you had a feature vector which is 156 number of entries in size. And you said you had used principal component analysis to reduce the size of the feature vectors.
Yeah.
So I was just curious, like by how much percentage did the size reduce by using PCA?
So we could reduce the size to up to 26 values only for the tactile sensor.
Okay, so from 156 to 26.
Yes.
Oh,
Yes.
okay, that's a big improvement.
Yeah, that was quite a big reduction and without affecting the results much. So yeah.
Okay, thank you.
Thanks.
Okay. No more questions? Last one. In the title of your paper, you say estimation of robust grasping. What is the meaning of robust, since you do not estimate the stability of your grasp, just the feasibility of your grasp? And my further question is, could we introduce a model to estimate the robustness?
So by robust, I meant that even if the grasp fails, the robot can reattempt. So the robot has some kind of knowledge about what is happening, and also with respect to object. And as you said, with this method and with the tactile values, it is very well possible to have some kind of model. For example, with the current approach itself, without doing anything, we can already see that if the grasp is not stable, object will move away from the robot hands. So by just capturing these predicted values, we can already see that the grasp is not stable and the object is moving. So yes, that is also a possibility.
Yeah, since you estimate the configuration,
exactly.
You have an idea of the stability or robustness. Okay, thanks. So thank you very much. We are going to move to the next presentation. Which is from Irish. Okay, we have you in line. So it is going to be about learning visual servo policies via planar cloning, and you will probably tell us more about that.
Thank you. Trying to share. Can I? Let's see. Need to allow sharing. System. So
Does it work?
Yeah, the security settings, Apple needs, Zoom needs permission. Yeah, doesn't have.
You need permission.
No, it asked me to leave the meeting. I will just try to rejoin.
It's his first time using the Mac to share. He has to restart. Yeah, restart soon. He's never used it before. permissions, yeah. I didn't. You could go to the next. He's going to restart his. Oh, I need to restart the laptop. No, just restart the application. Oh, the application.
Why don't we move to the next one?
We move to the next one. He's back.
Okay, let's see. Now I can share.
Oh, great.
Let's see. My presentation is here. So you can hear me and you can see the slides. Great. So my name is Ulrich Vieck and my collaborators are Robert Platt at Northeastern University and Kate Senko at Boston University. And I'm presenting learning visual server policies via planner cloning. So in our settings, we want to learn a pixel-to-talk controller. More specifically, we want to learn a control policy for achieving a desired hand pose with respect to novel objects in the environment. So this, we assume no context. So this complements very well with the first presentation, where we actually try to get close to a position where we then apply contact for the final manipulation. So this focuses only on the contact-free motion. For example, we want to move the cap on top of a bottle or a peg into a hole, or we want to move the gripper to a grasp configuration to manipulate an object. A popular approach is to use deep reinforcement learning to learn a control policy. The issue with that is that it assumes that it's an unstructured problem, and the sparse rewards are less informative than supervised learning, and the rewards are biased and have high variance. The idea is to use behavior cloning, which is a form of supervised learning. We first estimate the Q values using a full state motion planner in simulation, then clone the Q values to the observation space. In our case, it's depth images. And with that, we are able to execute on the robot without access to the full states. We propose panelized Q cloning. We assume we have a planner available in simulation that generates a trajectory without collision to the goal. And at each step, the planner experiences the same reward as it would do during deep learning. We roll out the planner from different initial configurations and glider configurations and generate a data set of observations, actions, and the Q value. Then we use supervised learning to clone to a Q function. So this approach is based on or combines existing methods and improves upon them. The first characteristic is that we use or we learn a value function instead of a policy with supervised value targets. That is similar to accurate. This allows fine-tuning using TD learning to improve beyond the suboptimal planner. And the second characteristic is that we penalize Q values for suboptimal actions, similar to DQFD. And that has this results in a policy that imitates the expert better. Finally, we augment the data set with all possible actions in each state, not just the action taken, and that helps to learn the values of suboptimal actions better. To train our method and all the baselines, we generate 500 different scenes with different glider configuration, peg size, pose of peg in the gripper, roll out 100 times from different initial positions to the goal. And we define success if we reach the goal goal state without collision or timeout. And the cost or the negative reward is a function of the distance moved, distance to obstacles, and collision. We train on the pack insertion task and the block stacking task. And it shows an example depth image in each of these scenes. We evaluate the pack insertion in simulation. And on top right, you can see the success on the training set. And on the bottom, the success on a holdout test set with different scenes. So the first approach we call batch PQC, where we generate the data set and then batch train. Then we have a variation, which we call online PQC. There we interleave expert actions on policy actions and training, similar to Dagger. We do that for all other ablations and baselines except for the DQN on policy. We look at 3 different ablations. The first is online PQC, where we do not penalize the Q values of suboptimal actions. That has the result that it doesn't learn to imitate the policy of the expert very well. Then the second ablation is where we only update the Q value for the action taken. That does not learn well the values of the non-expert actions. And then another variation where we penalize the suboptimal actions with a relative value. So we subtract a constant value. That doesn't perform that well than applying or setting just the suboptimal action to a fixed low value. And the baselines, so Dagger learns a policy directly. DQFD, that's the form of TD learning, where they add to the TD loss function also a large margin loss, where they penalize Q values of suboptimal actions that are not a margin lower than the optimal action. Then we have DQN on policy. So that does not have any guidance from the planner. So it's randomly exploring and actually never reaches the goal. So success rate is always 0. And then DQN, where we interleave expert rollouts and on policy rollouts. So on the pack insertion task, the performance on the training set is fairly similar, but on a test set, our approach is also similar to 2 baselines, the Dagger and DQFD. But if you look at a harder problem, the block stacking task, the performance, there's a big difference in the performance between our method and the baselines. You might notice the gap between training success and test success. So we were also interested into that, and we suspect that we need more training scenes, different scenes for the block stacking task. So we did an experiment with adding or training on more scenes. On the right, you see the success and the train success and test success for different amount of training scenes. And in particular for the block stacking task, there's a big gap. And it seems to be that the clutter is not only required to make the images visually more diverse, but also to learn collision avoidance. And for the block stacking task, it's also required to learn what the target should be, because it can be easily confused with the clutter objects. And you also look into fine-tuning with TD learning, because we learn a Q function, we can first train that and then fine-tune using just TD learning. And we see also an improvement beyond the suboptimal planner performance. And why would the planner be suboptimal? Well, it's planning in the full state, but during testing or on the robot, we don't have access to the full state. We only have camera images, and there we might have occlusions. So the planner doesn't really give the exact Q values, and also it does not. It's not according to the Bellman equation. So if we learn with TD targets, then we can improve beyond the suboptimal planner. We also did some proof of concept on the robot, where we run experiments on 5 different scenes. And you can see how the pack avoids collision with these obstacles. We transformed the images, left images, using a pix-to-pix scan to appear simulated. The real images, they have missing pixels, so it doesn't work right out of the box. And we achieve an 87% success rate on the robot. So to conclude, we generate the Q values using a planner with full state access, and then clone these values to the agent that can be executed on the robot with having just depth images. We learn a Q function, not a policy, and we penalize suboptimal actions that helps imitate the expert better. And we learn Q values of all actions, not just the action taken, that helps learning the suboptimal action values. And with TD learning, we can improve beyond the suboptimal planner. And we have shown that PQC outperforms ablations and baselines, in particular on the harder block stacking task. Thank you so much. Now I'm open for questions if we have time.
Yeah, thank you. What kind of resolution do you need in the depth estimation to make it work? Is it something critical?
The resolution of what?
The depth estimation.
Am I still sharing, by the way? I think I am. Ah, yeah. Let me just stop. The resolution of depth estimation?
Yeah.
So that images is fairly low with 64 by 64 pixels. And you mean the depth value?
Yeah.
Values itself? As good as the sensor can provide the values. Like it's in a sub, like maybe in a few millimeters accurate.
Okay. Other questions? Comments? No? Yes.
So that's probably very broad, but is there any advantage of learning directly a policy in torques rather than in position, joint angles or position of the end effector?
So here we learn the position in the end effector. And well, the advantage is that you can run the trained policy on any robot. You do the I'm unmuted, sorry. So the advantage of learning control in end position, an end effector position, is that you can run it on any robot after you train the policy. Because all the kinematics is a different issue.
Thank you.
Thank you. So we are going to move to the next presentation. So it is from Sandeep Shindala, and it will be about sampling training data for continual learning. Okay, we see your slide. full screen.
Can you hear me well?
Yeah, we hear you very well.
Okay.
Just put your slide in full screen. Yeah, okay. Without...
Good? No, without the preview.
Yeah.
I see. Swap displays. Okay, so now it should be good, right?
Yeah, excellent.
Okay. Yeah, thanks for the opportunity to present today. My name is Sandeep. I'm recently joined UT Austin as an assistant professor, and this was work done during my PhD at Stanford on distributed learning between fleets of robots and the cloud. So today we're starting to see fleets of networked robots ranging from low power delivery drones to Amazon Kiva manufacturing robots and even self-driving vehicles. And we're starting to place very high hopes and demands on these robots. So ideally we want them to be cheap. At the same time, we also want them to be very compute and power efficient. But finally, we also want them to be very autonomous, resilient in the physical world, and continually learn from their shared experiences. And this set of demands is somewhat at odds with the way we're building machine learning systems today. So we're building very accurate models that actually take quite a lot of compute to train, compute to run, and power reserves to run for real-time inference. And they also require a lot of labeled data in order to create very accurate models. So this trend is starting to become untenable for fleets of low-power compute-constrained robots. And a key question that many people have asked is, how do we actually scale? So can we actually build these cheap compute-efficient swarms that continually learn from each other and their shared experience? So there's been quite a lot of recent work in networked and cloud computing. And there's several benefits of using the cloud to offload both inference and real-time learning for robots. So one natural benefit of the cloud is if you have a compute-constrained robot, you can do some processing locally. But if you see a new image that is somewhat uncertain, you can query a larger computer vision model in the cloud. So this is real-time offloading, and we have prior work on that. But the focus of this talk is actually on distributed learning. So Intel estimates that a self-driving vehicle will measure more than 4 terabytes of rich video and LiDAR sensory data in just an hour and a half. So this, for one robot, amounts to about 1.9 million images. But now if you have a fleet of robots across the city, there's quite a lot of data. So there are rare events that they might measure, such as construction sites, rare traffic patterns, as well as weather conditions, that the fleet can continually and distributedly improve their computer vision models on. So the question is, how can we continually learn to maximize the accuracy of these computer vision models, but at the same time minimize end-to-end systems costs? So these systems costs start with the network. So network bandwidth consumption, how much do we upload? But they also manifest in terms of cloud storage, cloud computing time, and human labeling time in order to train these very large computer vision models. So the focus of this paper is on building a collaborative learning platform and system for networked robots. And the key technical question is, what is the right sensory data that each robot should sample from a very large video or LiDAR stream? So the work in this paper was actually tested on 2 data sets. And one of them was actually my commute data for about 6 months in the Silicon Valley. So every day I would, before going to grad school, I would just videotape my commute. And for example, in my iPhone, I might see a well understood freeway scene here, or I might chance upon a dynamic construction site, or even see a rare event, such as a self-driving car being tested on the road. So this is not a stock image, but it actually came from my dash cam. So today's systems in robotics would simply store all this data and naively upload all of it to the cloud, pay a lot for cloud storage, and use quite a lot of human annotation effort. Even to label a sub-select 1% of this data is very expensive, and use extensive cloud computing resources to retrain a model. And the benefit is that you can potentially compress and quantize this model back to a low power embedded device or an embedded GPU, and you can improve its performance on the next field test. So the key contribution of this paper is to build a lightweight sampling algorithm in Gray. And it learns to reject these well-understood freeway scenes and just harvest these interesting training examples so that robots can quickly learn, but with minimal end-to-end systems costs. And we're framing it as a problem in decision theory, where given any new sensory sample, the robot needs to estimate the marginal accuracy gain if we're actually going to upload this sample and use it for training, and weigh that with the system's costs that incorporate local compute, the network, and the other systems costs I described. So just to preview the results, which are detailed in the paper, they were tested on about 6 months of my commute data. And this sampling algorithm in gray that I alluded to actually runs on a low power deep learning accelerator. So this USB stick that I'm pointing to is the Google Edge Tensor Processing Unit, or TPU. It consumes about 2 to 4 watts of power. So a cloud grade GPU would consume about 200 watts. And it's doing some very minimal overhead decision making to figure out whether to cache and sample a new image that we see. And we reduced the number of images that are sent to a human for labeling by about 80%. So the first question of interest is, why should we specialize computer vision models? And why can't we simply just use all field data? So again, this is a picture from my commute of a construction site, and it's passed through a pre-trained or default computer vision model called COCO. So COCO, which stands for Common Objects in Context, it actually pervasively mislabels all these traffic cones that I'm pointing to as people. But this very large excavator or construction vehicle is neither like a bus nor a car, so it's actually completely missed. And on the right is a domain-specific computer vision model that we retrained using automatically sampled data from my commute. And you can see that it mitigates these errors. But actually, every image from the field is very expensive. So this is an image that we actually paid Google to label from our commute. And you can see that even one image has over 20 bounding boxes, and the numbers quickly add up. And then, of course, there's network and storage costs as well. So even though we might want to subsample sensory data, it turns out this problem is rather hard. So just to take a toy example, let's say you know that your computer vision model using offline data performs poorly on construction sites, or just for fun, you might want to recognize self-driving cars being tested on the road and differentiate them from regular cars. So you can start with a small seed data set of problem examples and use transfer learning in order to train a nominal computer vision model and sync it to your iPhone or Edge device. But it will be rather poor initially by virtue of having a small data set. So the problem that you face is now you've synced this to your robot or iPhone, and you see a very large stream of video. And using this poor detector, you need to describe or decide whether to sample a new image. And it turns out that there's an explosion of possible samples one could take. So if you ask a simple question, given 15 minutes of video that is subsampled at 5 frames per second, if I can only select 2,000 images, what are the most useful images to select? It turns out there's a huge possible explosion of samples one could take. So it's not at all intuitive how to sample these sensory data. So typically this realm of subsampling data to improve a learner has been discussed in active learning, but it turns out today's active learning metrics use very complex uncertainty metrics in their acquisition functions to guide whether a new sample is worthy of caching. So typically they use Bayesian deep neural networks, which have a distribution over model parameters. And they use that to figure out a metric of uncertainty to guide whether to cache an image. But it turns out that on really resource constrained robots, such as the one pictured here that we built with a Raspberry Pi and an Edge TPU, you can't cache a distribution of model parameters. We just have 8 megabytes of on-chip memory. And each forward pass or inference of the neural network is very slow. So conventional active learning won't work for our problem. And the key difference in the algorithm that we describe in the paper is that we actually keep the local computation very lightweight and simple, but we actually delegate the compute heavy tasks to the cloud. So the key insight that we have is you can train a neural network and calibrate its uncertainty in the cloud, sync a couple of hyperparameters to the robot, and essentially build a low weight data-driven filter at the robot that guides what data to sample. And so in the rest of this talk, I'll just give a preview of our algorithm, but the details are actually in the paper. So in this block diagram on the left is our robot, and on the right is the cloud. And we start with a couple of targets. So these targets are task-relevant concepts that we have very little training data for, but we want to map to the robots in order to accrue more data. And the key question of interest is, what is this sampling policy pi sample in green that will maximize accuracy but minimize systems costs? So a robot might see T images per day I, and has a limited cache, limited by N cache, that limits how much it can upload per day. And the goal is to find the best sampling policy pi that maximizes your accuracy after N days of learning. And just because we're sampling data to the cloud doesn't mean we need to delete it on board. You can still cache it, right? So the first part of this algorithm is to actually define a set of task relevant images in the cloud that you want to accrue more sensory data for. So that's denoted by the target set. In our example, it could be images of self-driving cars being tested on the road, or these hazardous construction sites that are poorly understood by our current computer vision model. And that is an initial seed data set called D0 for round 0 of training. And in each round or day I, we have a new computer vision model that concretely maps an image X of T into a set of outputs Y bar of T, which are essentially the bounding boxes, confidences, and embeddings. So the key question of interest here is, what is an app sampling policy that takes some sort of parameters or feedback from the cloud about how to discern whether a new image is signal or noise. So these are given by the hyperparameters theta of I. And the key idea here is, let's say I have a huge video stream in blue and I want to sample the image in red. All I have at my disposal are the outputs of the computer vision model, and I need to design an action A of T to sample or not. And when you train this neural network, even though it's a quantized compressed neural network, you can use a variety of metrics to differentiate what are the embedding scores or the confidence scores or other metrics between signal, which is in red, so your task relevant images of construction sites, and background images that you know well, which are in blue. So you can build this filter and calibrate its uncertainty and sync these cutoffs to the robot, which are used to guide sampling. So essentially, we can build a very simple decision rule guided by these hyperparameters to decide whether a new image is worthy of caching. And that's the sampling policy in green. And the next step is, once you have used this policy to populate your cache of images, you can upload them to the cloud, get selected labels, retrain your model, and the process will continue as usual. And you continually retrain your model. So the key idea here is, once you have a new computer vision model in the cloud and nominally new data that's added to it, you can recalibrate your thresholds. So on the left is day 0, and there's quite a lot of uncertainty about what differentiates signal in red from background images in blue. But by virtue of running this algorithm on the right, by day 10, you build a sharper filter. And you can sync these hyperparameters back to the robot, and the process will continue. So this is just an overview of the algorithm. You build these filters, sync them to the robot, use them in your decision rule, and upload data to retrain the computer vision model. So I'll just wrap up with some preliminary results of our work. So the first data set was, again, on 6 months of my commute data. And our system is called HarvestNet in bold orange. So it beats conventional active learning metrics that don't use feedback from the cloud in red. And it's fairly close to an upper bound Oracle solution. And on a more challenging domain of construction sites, by virtue of using this cloud feedback, we're able to improve accuracy with fewer days of training. And we drastically reduce systems costs. And just to show that our method generalizes, we tested it on a small mobile robot to recognize different indoor scenes and objects and different people in the lab. And the same results hold. And yeah, this is just one of our recent works that we're working on inference learning and control in 5G networks. So this year in Coral, we have a paper on actually expanding this work to a decentralized peer-to-peer data sharing platform. And we also have a paper in Europe on extending some of these ideas to figure out what is the right representation of data for both inference and control. So for that, I'm happy to take any questions. Thanks.
Okay. Questions? How can you be sure that you're not introducing catastrophic forgetting when you update your data or your model? And conversely, how can you be sure that you get the right information for the system you want to deal with? I mean, for the navigation system, obstacle avoidance and things like that.
Sure. Yeah, that's a great question. So firstly, we're not deleting any data, right? So we keep all of our data at the locally at the robot, and only a sub-selected amount is used in the cloud. So we can calibrate whether we need more data if our task changes. Let's say we don't look at just navigation tasks, but we look at a different domain. You can run this algorithm again to sample data for a new set of task relevant images. But the goal of this to continually improve your model is actually to mitigate catastrophic forgetting. So you have a data set that's continually added to in the cloud. So you retrain on the new data set that's larger than on round zero. So you're actually expanding your data set and training on all of it in order to mitigate this forgetting phenomenon that happens in a lot of neural networks.
Larger is the data set, the better is the model. Am I right?
Sorry, could you repeat that question?
The larger is the data set, the better is the model you built.
Yeah. That's what empirically we're seeing. Okay. Yeah. So actually, go ahead. Sorry.
We have another question.
Yes. Hi, great work. Thanks for explaining it, and very eloquent explanation. So I was curious, it seems like there are two goals of your work. First is to reduce the amount of data that you're using in order to train on, and the second one is, of course, to increase the accuracy on novel cases. The first one is what I'm interested in. You said that you reduce the amount of data that you're uploading by 80%. Could you quantify that against how common these circumstances, like what is the reduction on so-called common circumstances, or some other kind of, comparison of whether that's good? I mean, of course, 20% from 100 is better, but what would be your ideal there?
Yeah. So that's a great question. So quantitatively in the paper, this 80% number is if you used every frame of video, how much data would you require compared to what arises from our sampling algorithm? Okay. So there are other metrics that we also provide in the paper. So those curves I was showing where you have the accuracy versus the days of training, every algorithm I was comparing to, which is conventional active learning as well as random sampling and Oracle, every day you only have a cache limit of 100 images per day. So every data, and then the way you quantify that is you only want to upload, say, 1 to 5%, because you have a maximum cost that you're willing to spend on the network as well as data labeling. So does that answer your question?
Yeah, that's very helpful. So basically you're saying you're conditioning your answer on a certain budget of what you can upload, and so the results naturally fall from there. So thank you.
Exactly. Yeah, so we start with systems cost and then derive the algorithm given that constraint.
Okay, no more questions. So we have to thank you for your presentation again. So the next one will be given on site. We are going to learn how to play with food. Is it correct?
Hello everyone again, I'm Kevin Zhang, and today I'll be presenting our work on playing with food, learning food item representations through interactive exploration. So first of all, food items all have differing material properties. Mask off, okay, yeah. Okay, food items have differing material properties depending on how they were stored, how they were harvested, how they were cooked. And different food items are juicier or softer than others. And us humans, we have intuitions about what food items' properties might entail just by looking at it. And that's mainly due to when we were babies, we learned food properties when we were playing with it. These food items could be very important for robots because different skills like grasping or trying to flip might benefit from adapting their skill parameters or choosing a different skill based on what food properties they might be expecting. So our plan was to use these embeddings that we will learn to train skills to figure out which skill and skill parameters to use in the future. But for this paper, we mainly focused on having the robot interact with the food items to learn properties. Yeah. Okay, so some related works are, several works have tried to learn deformable object models in simulation, either like deformable cloth or pouring of granular material. Another set of related works are on interactive perception. So like Sinapov et al. Have used vision, audio, proprioceptive to information to classify and locate objects. Finally, there's been other works on learning object embedding representations. So these were mainly from visual information. Using a large data set of items, they would train embeddings and then use those embeddings to retrieve images based on what characteristics they were interested in, so ripe to unripe objects or raw to cooked items. Our approach is focused on using real robot multimodal sensor data collected through interaction and training the embedding network that way. So for the pipeline, we first collect multimodal sensor data both during the robot cutting process as well as the robot playing process. Then we train an embedding network. So this is a self-supervised way using a triplet loss. I'll go into that later. And then finally, our embedding network takes in a vision overhead camera and outputs an embedding. And then our plan is to use the embeddings to train other classification networks depending on tasks. So first of all, some of the, videos aren't playing. Okay. So during the robotic cutting, we have 3 RealSense cameras, one on the tongue, one on the hand, and one on the side, as well as the overhead connect. And we also have 3 contact microphones. This allows us to hear the robot as it's cutting. So there's one on the knife, one on the tongue, and one underneath the cutting board. We vary the slices based on slice thickness and slice angles. And then we also cut 10 slices off each type of food item. For robotic playing, hope this can hear. Okay. Yeah, so during robotic playing, we again have 1 RealSense on the side, 0 Connect overhead, and 2 contact microphones. And the process is it first pushes down on the object to check for like compression or hardness, then it grasps it and finally releases. And we have some fake finger vision on the robotic fingers. So this is different from the normal one because it uses a polycarbonate fingertip instead of a gel. So overall, our types of sensors collected are visual from all the cameras, audio from the contact microphones, and then proprioceptive information from the robots, so the end effectors, forces and positions, as well as the grip width. Here's some sample data comparison. Sorry, can you, the audio doesn't seem to be working. Yeah, okay. So here I'm, okay, let me play it again. Okay, so from audio, we can gain quite a bit of information about the food item. So when these two contact, you can kind of tell they're hard. Meanwhile, the steak is softer, and From the force data, we stopped the robot from pushing at 10 newtons. Here we can see the camera views from the finger visions. I don't think simulation can replicate that one. And then here we can see like the tomato being crushed, releasing juices. Finally, when we release, there's also more audio information that we can tell. So whether it's like a softer on impact or like this onion, you can hear has different material properties. So to learn these embeddings, we use mainly ResNet and then some linear layers to get an embedding of like around 60 features. This is used for classification and regression tests later on, but to first make the self-supervision possible, we create triplets. So triplets are, we have one anchor, one positive, and one negative. So from the audio features, it's kind of simple to find close ones because the audio, we use lib-rosa and MEL frequencies, septual coefficients to get the features in discrete form. For the food type, that's just the food class. And then for the proprioceptive features, we just use the raw data of what the final gripper width was, the final position of the push, and the delta between when we first contact the item and when we finally reach the 10 Newton threshold. Once we get those embeddings, we train the networks to predict several different tasks. So first is juiciness and hardness. This one we leave one out, so whichever class we're testing is left out of the training. There's a cooked versus uncooked. I'll go into that later. Then there's food type and slice type. So slice type is like how we varied the slice thickness and angle. And finally, the regression was the final gripper width. So as a result, we can see that our baselines are ResNet trained to directly predict the class, while everything else uses our first embedding network to get the embeddings and then using the embeddings to train the resulting classifiers. So ResNet performs very well on food type accuracy. ResNet is pretty good on object detection, and but on all of the other tasks like hardness and juiciness, we see that our embeddings can improve on the ResNet baselines, although they still aren't great. And for slice type in particular, it had a higher percentage than the ResNet by 10%, which shows that implicitly it learned something during that embedding, but it's still not perfect. However, when we look at this cooked versus uncooked data set, we had 8 items that were cooked and 8 items that were uncooked. The cooked ones were boiled for 10 minutes. You can't see the labels, but the purple and yellow are pear and apple. They are pretty similar food characteristically. And when they're boiled, they also end up clustered together. And when we ran the same studies as well as the cooked accuracy, our embedding networks for the audio network and the proprioceptive performed much better than ResNet as a whole. So our key takeaways were that these embeddings that were trained self-supervised with the triplet losses based on the audio and proprioceptive were able to outperform the ResNet baseline, which showed that it was able to capture some similarities between the different food items more than the ResNet when trained directly through. I'd like to thank all of my collaborators and Sony AI for funding this. And this is mainly a data set paper, so we have all of our data at the website above, and that's my email. Thanks for listening, and if you have any questions.
Well, we have time for 1 or 2 short questions. No? Yes.
Have you looked at any biosensors that you could use, like ethylene is a good indicator of food ripening, or some other sort of sensors that you can add it to this?
So I think following this work, another work used spectrometers. He just joined CMU, so maybe we'll borrow his spectrometer. I think it was pretty expensive. The finger vision I made was just like a USB camera and some metal and a plastic on the top. But yeah, I think more sensors could be useful, but it also adds some extra overhead, I guess, and like, yeah, it's hard to say.
Quick question, since you said this was largely a dataset paper, I'm curious where people have taken this since the dataset has been published, or is it recently published and you're still waiting? I'm curious what you're hoping people could use this for eventually. I'm assuming maybe cooking robots, but maybe other applications as well.
Yeah, so my plan was to use these embedding networks and have the robot like determine when to flip steaks. I guess I skipped the slide. But we also had we haven't incorporated a lot of the finger vision camera data yet, because the data was just so variable depending on the food item. We also had spam that was kind of gross, but we have created masks to try and define it. But I think my next work is using the embeddings, figure out how to or when to flip items, along with the thermal cameras used as an indicator as well, but that's future/current work.
Thank you. Okay, thank you, Kevin. Thank you again. Okay, we have another presentation, which will be on a completely different topic, because we will speak about data-driven design controllers for under and actuated robots, and it is this presentation will be given by Wang Kung, which is online. Do you hear us? No.
You can't hear me?
Oh.
Can you guys hear me?
No. It works.
Can you hear me? I'm not sure if you can
perfectly.
Hear me. Okay.
And can you put your slides in full screen? That's perfect.
Is that good?
Yeah, go on.
Alrighty. So thank you very much, everyone. My name is Juan Kuhn, and today I'll be presenting my work called Data-Driven Design of Energy Shaping Controllers for Swing-Up Control of Under-Actuated Robots. And this is a joint work with me and my advisor, Aikut Satishi. So the main idea in machine learning of using machine learning in control applications is to essentially find a control system that optimize some sort of reward or loss, right? But while also incorporating the physical structure of the system. And the learning loop is typically done offline. And there are many ways to do this. And one of the most prominent way is probably reinforcement learning. And the main idea, there are many variations of reinforcement learning, but the main idea is to we observe repeated interactions with the environment and try to make sense of what the environment actually is, right? So there's a step where we fit a model and estimate the return or the cost to go of function. Then from that information, we improve upon the policy, the control policy, and then we repeat this process over and over again, right? So one of the main challenges with reinforcement learning is that in most control system applications, we do have some knowledge of the actual system, right? We know pretty well what the model is, what the equations of motion is, for example, and we want to inject that somehow into the learning scheme. And it is kind of difficult to do that in reinforcement learning. And also another challenge in reinforcement learning is that because we can't inject information into the learning scheme, the sample complexity becomes really high. So we require a lot of data for training. And the resulting control policy may or may not be interpretable at all in terms of, okay, what this term is actually doing to the dynamics, right? So the motivation behind our work is to combine the flexibility of machine learning approaches with some well-known technique, in this case, passivity-based control, to come up with a data-efficient learning framework that can find control policies for under-actuated robotic systems. And I'm going to give a little background on passivity-based control. So suppose you have a mechanical system with the Hamiltonian of this form. So it's quadratic in the momentum, and V is the potential energy. M is the mass matrix. So with this Hamiltonian, the dynamic is given as the symplectic gradient of the Hamiltonian here. And we assume that we have a control input U, and G is the known input matrix. Right. So the goal is to design the function U and such that the closed loop system is passive with respect to some storage function HD. So what that means is that we want to transform the dynamics of the system such that the closed loop takes on a different type of Hamiltonian that is HD that we define. And typically in this setting, the control function is broken into one energy shaping term and one damping injection term. Another requirement that we require of HD is such that it has a minimum at the desired equilibrium Q star and with zero velocity. So one of the more popular type of PBC is called IDA PBC, or interconnection and damping assignment PBC. In this case, the closed loop Hamiltonian is chosen to be of the same form as the open loop. That is, it remains quadratic in the momentum, right? And with this HD, the control action U is comprised of these terms. So the energy shaping term is given here, and the damping injection term is given here. So essentially, it's just a combination of the gradients of the desired Hamiltonian, or HD. And how do we, the main task is then, how do we choose these MD and VD such that the closed loop system actually obey this form of Hamiltonian, right? And doing this requires, unfortunately, solving nonlinear partial differential equations, a task that is generally very difficult to do, right? So the idea is to use machine learning to ease this task a little bit, right? So the main objective is, the problem statement of our work is to, given a dynamic system of in the control affine form, right? We want to approximate the desired Hamiltonian HD with a neural net, right? And we want to learn an HD such that the closed loop system perform some desired task, right? And we'll take the control input to be a linear combination of the gradient of HD, which is a typical thing to do in passivity-based control. So we essentially find this neural network, right? The main problem is then, how do we train a neural network so that it performs the task that we want it to do? And I'll describe it here now. So essentially, we formulate a control problem as this optimization problem. Given a running cost R, right, we want to minimize this running cost, which is a function of phi, which is the flow of the equations of motion, right, subject to the dynamics of the dynamics of the system, some initial condition, right, and the control input is taken to be of this form. Now, the dynamics of the system is encoded in this phi here, because phi is the flow of the equations of motion. And running cost function is designed. Well, I'll talk more about that in the following slides. And H theta is a neural network whose input is 2n dimension, and the output is a scalar. So the running cost function consists of 3 terms. So one is called R perpendicular, or R per for short. R set is the set distance to a desired goal set. R reg is a regularization term. So R perp is designed such that, let's say, if you happen to have some preferred orbit or trajectory that you want the control system to follow, right, you can inject this term. This term is designed to accommodate that, essentially. So for example, if you have gamma star that can be obtained from perhaps a motion planning algorithm or trajectory optimization, we want to penalize the controller whenever it spends time away from this orbit, right? And one difficulty is that it may not be obvious how to compute the distance from that orbit efficiently, and we do that by using transverse coordinates. So transverse coordinates mean essentially, let's say you have this orbit in red here, and we want to follow this orbit, and we want to converge to this orbit, not in time, but in configuration space. And how do we compute how do we compute the loss based on how far away you are from this orbit, right? So one way to do that is to use transverse coordinates. So first, what we do is we define a family of Poincare section S here, right? And we can picture this as a moving Poincare section that moves along the orbit. And we'll parameterize these section by tau, which acts as a surrogate for time, and it kind of gives you the information of where along the orbit the current state is in. And then we'll define a new coordinate that's perpendicular to the orbit in this plane here, in this Poincare section. And note that when xperp is 0, right, because it's perpendicular to the orbit, when xperp is 0, it means that we are actually on the orbit. So we'll use this as the loss in our cost function. But this rperp term is this rperp term here is optional. We just designed it to accommodate some preferred orbit because, for example, the pendulum for a pendulum system, there may be the homoclinic orbit, for example, is something we want to follow, but not every system has a desired orbit. So this term is not always required. Okay, the next term is rset. This is the main loss that actually takes us to the desired equilibrium. So this term is designed as a set distance to a some set near the desired equilibrium x star. So it's defined as this equation here. And S is, for example, S can be chosen as, for example, a ball with radius r around x star. Right. So essentially, it says that if you are within a radius r within a radius r of the desired equilibrium, don't add any cost. And if you're further away from that, please add some cost to the loss function. Right. So the main difficulty is now, okay, we have a loss function. How do we actually make improvements of the parameters towards something good, right? Because remember that our cost function here depends on phi, depends on the trajectory of the data of the system, right? So we use what's called a recent development called Neuro ODE that essentially brings in adjoint sensitivity analysis to find the gradient of the loss function that depends on a solution of a differential equation, right? So we have a differential equation that we're computing the loss based on its solution, and adjoint sensitivity analysis allows you to do that efficiently. Essentially, what we do, and I'm just going to give a quick summary of that method here. Essentially, we define another ODE. In this case, it's called the adjoint problem. And we solve this adjoint problem backwards in time to obtain the gradients, right? And the details is given in the Neuro ODE paper. And once we solve this differential equation backwards in time, the gradient of the loss function is defined as this equation shown here. And this method is based on Van Turgen's maximum principle. And yep, we use this method to compute the gradient, and it's great. So let's go to, so I have some algorithms here that's also detailed in the paper, but since we're pressed on time, I'm just gonna skip it and explain it in picture instead. So in this case, what I'm showing here is a homoclinic orbit of the pendulum with minus pi and pi as my desired equilibrium, right? So our training algorithm first start off with a trajectory that is initially poorly trained, right? So the system start off over here, whereas we actually want to go to this shaded area over here or over here. But initially, since the weights are randomized, it's not doing well, and it's actually going down towards to the wrong equilibrium, right? So how do we sample? How do we decide what initial conditions to generate the trajectories from in order to compute the loss? So first, we use the idea that's very similar to Dagger. So essentially, we start off the system on policy, which is initially poorly trained. We'll sample points along this trajectory, as shown in yellow, and then we'll use these points as the initial conditions to compute the loss from. Right? And we do this repeatedly until the learn policy actually do something reasonable, and after which, right, we stop the training after we hit a certain amount of tolerance in the loss. Here we'll show some results. We did experiments both in simulation and on the physical systems. And in simulation, we use the learn controller to perform the swing up, starting from a bunch of initial conditions x naught, and we use the standard LQR controller to catch and stabilize the swing. In the physical experiment, we start the robot from downward equilibrium with a small disturbance, and so this physical experiment, since our system, we don't have perfect knowledge of the model parameters. So what this experiment will show is that it will demonstrate some robustness properties of the learn controller based against model uncertainties. So with the pendulum, we have this dynamics, right? And the desired equilibrium is plus or minus pi. And we'll define the goal set to be some ball of radius 0.1 around plus or minus pi. And the desired homoclinic orbit is given by this equation here. So this figure shows some training progress. So initially, with randomized weights, the controller does really poorly, right? It doesn't do anything at all. And as the training progress, we see that the trajectory is starting to converge closer and closer to the homoclinic orbit, and eventually brings the state near this desired equilibrium here. And at which point, once it becomes close enough, we switch to LQR and catch the swing. And here's a recorded trajectory from a physical run. And we see that even with some uncertainties in the models, our controller still does pretty well, and it still swings up the pendulum as decided, as is shown in simulation. So this suggests that there is some inherent robustness properties using this method, right? And we did another experiment also on the cart pole, which is a little bit more complex. So instead of just the pendulum, we have a cart and a pendulum. So the force is acted on the cart, and the pendulum is just passive. It's not being actuated. Right? And here, the dynamics is shown here. And what we want to find is how much force we want to act on this cart in order to swing up the pendulum. And in our physical system, we are actually constrained to the cart is actually constrained. It essentially has track limits of some amount XUB, right? So the neural network controller has to be able to account for that. And in the experiments, we see that the neural net controller performs well. It swings up and it's able to stabilize without going over the track limit of 0.4 here. And here's just a comparison of the energy shaping control of the learn controller with traditional energy shaping techniques, right? So if we compute the loss of the trajectory, the quadratic loss shown here, starting at different point on this grid here, we can see that in general, in pretty much all initial states, right, the learn controller accumulates less cost than the energy shaping controller in order to perform the swing up. So what this shows is that not only we can, mimic, we learn a Lyapunov-like function, we also learn a Lyapunov-like function that also accumulates less cost to perform the swing up task than traditional energy shaping techniques, right? So these, one more figure here. So HD this is the learn function, right? And our controller is taken to be the gradient of this function with respect to the input. And we see that it has a nice quadratic-like shape. So this looks a lot like a quadratic function that, so the next step of our research is can we infer any stability property from this learn function here, right? Because empirically, it looks like it qualifies as a Lyapunov function, but how do we make sure that it's actually a Lyapunov function and the system is stable, right? So that's the direction of where this research is heading, and we're currently doing some work in that regards. But that concludes my presentation. I'm happy to take any questions at this time.
Thank you for this nice presentation. Do we have questions? Yes, one here.
Okay. Very nice work. I'm curious about, so you have tested this algorithm with a 1 degrees of freedom system, fully actuated, and with a 2 degrees of freedom system with 1 degrees of actuation. So I wonder,
Correct.
how do you think this will scale up with some more higher dimensional system, where maybe, or even already with a double pendulum, that it's also properly chaotic while...
Yeah, that's a great question. We actually are building a double pendulum, an acrobat, in our lab right now, and we're in the early stage of testing. But in simulations, it's this framework is actually it's swinging up the acrobat perfectly well, but we don't know how it will perform with model uncertainties, because an acrobat, right, is very sensitive to model uncertainties, because when the double pendulum is unactuated, it's chaotic. So if you're just off by a little bit in terms of model parameters, there could be some problems. But yes, we are doing some work to extend this to higher degrees of freedom. So an acrobat is essentially a pendulum, a double pendulum with the second joint is actuated, but the first joint is not, right? Like an acrobat. So.
You could also try on large-scale dynamic systems like flow control, on computer fluid dynamics. Yeah, I think it would work also.
Yeah. We haven't tried anything larger than four-dimensional state space, but yeah, we just don't have the means to test it in the lab. That's anything that's larger than that, right? But it should work because passivity-based control, right, as we know, is being applied left and right in high-dimensional systems all the time, and this follows a similar idea. So in theory, it should work, but we haven't done that research yet, so we can't say anything in that sense.
Yeah, another question?
Yes, thank you very much. My initial question was the same as my previous speaker, but maybe in the same sense.
Yeah.
How does the training effort scale with the dimensions of your dynamical system?
Right. Good. Thank you. That's a great question. So with the pendulum, right, is the 1 degree of freedom with limited torque. That trains in 2 or 3 minutes, right? Because the neural network that we use to do this is basically just a function approximator, and we don't need anything large at all to do the training. And it is kind of hard to say at this point how it will scale with larger dimensional system. But going from the pendulum to the card pole, right, that did not increase the training complexity at all. So it still takes 2 or 3 minutes to train the card pole system, which is, in this case, the state space is 4-dimensional rather than 2-dimensional, and the training times takes in the 2 or 3 minutes still, and we keep the neural network size the same. In systems of, say, 29 degrees of freedom, I foresee that it's going to take a lot more training effort in terms of training time, and actually how we sample the state space is going to be more complex. But I don't have a clear answer of how it will scale up in that sense, but it will definitely go up.
Okay, we're going to move to, thank you again. Thank you for this very nice work. We're going to move to the last presentation of the session and of the day.
Maxwell.
Which is Maxwell on site about recurrent neural network for the raw estimation of a needle steering. You have two minutes. Tack. take the mic, I guess.
All right, thank you everybody for staying around for the last talk. I'm excited to talk to you guys about recurrent neural networks used for estimating incomplete sensor data as applied to a needle steering system. And so this is a project that's been going on for a while. I wanted to start off with the motivation. So talking about cancer, lung cancer is the one with the highest death out of all of them, affecting both male and women. And the only way to really diagnose this definitively is to get a biopsy. And so getting a biopsy from a patient implies that you need to be able to reach the tumor. And so there's two main ways that you mainly do that in medicine. One is transpercutaneous, where they usually under CT guidance will deliver a needle across the chest wall. Unfortunately, this is a very risky procedure, results in about 20% pneumothorax, which is lung collapse, and the diagnostic yield is low. They don't get it if the nodule is under a certain size in about 50% of the cases. The other approach is transoral, going through a bronchoscope. So this is using an endoscope to try and reach through the bronchial airways into the lung. Again, this is a low diagnostic yield for small diameter tumors, and furthermore, they can't reach into the periphery of the lung, so you're limited by the scope size. With nature, unfortunately, the tumors occur in the periphery of the lung, and with this method, you're constrained to only the green areas. So this is a technology that's been developed in my lab called steerable needles, and so here we can see in gelatin delivering a needle in different trajectories, and so you basically control it by inserting and rotating the back end of the needle. And this is gelatin. It's a phantom that we use typically just to test needles. And so basically, the idea is you have a target shown in red. There's a bevel on the needle. And so the tissue forces that are applied to the bevel surface cause these very flexible needles to deflect laterally. By rotating the bevel, you can steer it to the target. This is really non-intuitive, though. You can see this is being done with a short needle and by hand. When we deliver these through endoscopes, we require a robot to do it. So the concept for the system is you deploy the endoscope down following a pre-planned trajectory. You puncture out through the airway wall. The target is in yellow there. And you deliver the steerable needle into the lung parenchyma, or the negative space of the lung. This is the prototype that we've built in my lab. It's basically deploying through a clinical bronchoscope. And you can see the robotic actuation unit on the back end. It consists of a couple of carriages that can both insert, translating each of the tubes in the assembly and rotating them. This is what the tip looks like. So there's a tool channel on the scope. We have a series of nested tubes. The outermost is a therapy delivery sheath that will be deployed over everything in the end. There's an aiming device that allows us to locally aim the steerable needle when we're close to that puncture area. Exiting the bronchial wall, and then the steerable needle is the final one on the inside. And so my talk today is going to focus mostly on the steerable needle here. And so on the right here, that's not a rendering. That's a segmented CT scan anatomy of a pig lung. And you can see this is a very obstacle-dense environment. All of those colored things, we don't want to hit them. There's a cost to hitting them. It's bad. Furthermore, we don't want to exit the lung, right? So that's that pneumothorax. If you exit the bounding lobes, you cause the lung to collapse. Furthermore, everything's squishy, and registering to it is really hard. But how we can kind of do our best job to navigate this complex environment is to embed sensors in the needle. And so that blue sensor there is an electromagnetic tracking sensor. We do not have line of sight. We wish we had LiDAR. We wish we could do everything that we could, but this is all blind, especially when we exit the bronchial airway. We are completely blind. And so electromagnetic tracking is the best we can do. Furthermore, with lung tissue, it's very, very soft, and we're relying on tissue forces to deflect the needle. So what we've done here is we have a helical laser pattern that we've applied to the needle backbone using laser cutting, and a flexure hinge at the tip. And this serves to reduce the bending stiffness of the needle, such as to get the most deflection that we can for that given tissue force. However, so here you can see a video. It's basically a floppy noodle at the end of the day. This goes from being a nitinol tube that is solid and has is still very flexible compared to steel. But on this colored graph here, this is the hysteresis plot of how, for these needles, when we change the rotation on the back end, how that transmits the rotational motion to the tip. And furthermore, the color displays the effect only just due to inserting it into the tissue. So this is plotted in gelatin, but with the blue, you can see that the plateaus on the bottom start at like 90 degrees of lag before you start to see transmission of motion to the tip. And then as you get up to 70 millimeters of insertion, that roughly doubles. Furthermore, the kind of shape of the hysteresis curve kind of changes and it becomes less idealized because there's effects of static and dynamic friction. So this is all to say it's pretty hard to model. And most of the models that we use to control these needles are fairly simplified. So this non-holonomic unicycle model is conventionally used, and this makes analogy to a unicycle rolling on a bending plane. So the bending plane is determined by the bevel orientation. And so as the needle rotates, that bending plane changes. But it's a one-parameter model that's from pre-calibration of figuring out what that radius of curvature is that the needle will process about. But this basically means that the needle cannot instantaneously move laterally. It has to kind of obey that rolling constraint by analogy. But the assumptions in those models are that the motion is transmitted to the tip instantaneously. And so in this system, we have a lot of torsional lag. And so basically this means that the rotational input that we apply at the base does not equal the rotational input that we get at the tip. And this results in dominating the kinematics or the dynamics of the needle because it's neglecting all these frictional effects. So furthermore, these needles are pretty long that we deploy through these endoscopes. The endoscope itself is 900 millimeters long, so the needle itself is over a meter, only a millimeter in diameter. There's endoscope interaction forces that are hard to sense. We have tissue friction effects, and the laser patterning that we apply to the needle further makes this problem harder. So really what we have is this torsionally lagging needle that our models don't work well on. So we have those electromagnetic sensors that we can put in the tip, and so that helps a lot. And so up until now, we've been using the sensors on the right. They're a full 6 degree of freedom sensor, but you can see the one on the left is about half the size. And in medicine, we really want to be able to miniaturize the size of our devices because it's less invasive, but we do not want to sacrifice accuracy, right? And so the tubes shown there are the corresponding needle sizes of what those sensors will fit into. And so we're going to formulate a problem using a supervised learning problem and try and apply machine learning to help us out. So the input vector that we have here is the position PK at every time step of the needle sensor at the tip, along with the axis, eta. And then we encode the rotation at the base by alpha using sine and cosine to kind of bound it. And then what we're asking the network to do is predict the tip angle theta. So once we can predict the tip angle, we'd like to be able to incorporate this into our closed loop control. So we use a sliding mode controller that is going to take a target point. It's going to prescribe control inputs to the needle system, the physical system. We are going to sense partially our state using the electromagnetic tracking, feed that to our LSTM-based state estimator, and then we're going to have it reconstruct the state with its estimate and the sense state, giving that back to the controller, trying to steer this autonomously. And so, right, we use an LSTM architecture. We have a data set that's composed of these steers, data pairs, X and Y. We have a neural net that is composed of its priors that are from the training data set, along with the learnable parameters pi. During training, we want to find the optimal learning parameters that minimize some loss function over that data set. The loss function that we use is simply the mean squared error at every time step k, I in this one. And again, those are the input and output vectors that the network is taking and predicting. And so this is what we're after. We want the roll angle of the needle to be used. So for our training data, I collected 300 point targets, 300 steers to different point targets that were both sampled through a grid and uniformly randomly sampled in gelatin. And so on the left, those are the steers. This was sampled with the 6DOF sensor inside of it. So we have our ground truth to compare our accuracy to. And so we want to look at how this performs well online. On the top, we have histograms of angular error. We compare it to using our learn method to a standard Kalman filter that's relying on that non-holonomic needle model that has no notion of the deadband. And we can see that it doesn't perform well, which is not surprising. The torsional dynamics dominate how the needle moves in this case. On the bottom, really what we're after is accurate targeting error. And so this is like being able to reach the nodule or the intended target accurately. And so this data is all the same. The stuff on the right is that small little box blown up. And we can see over, I think, 30 steers, different targets. 30 targets or so we're achieving under 0.5 millimeter targeting error, which is within clinical standards. So, right, this was all in gelatin and brain, and we want to be able to apply this to lung, which is the tissue that's the hardest. And so this is our setup. We have a CT scanner that gives us the anatomy. We have an EM tracker on that tripod there. That's the one that's doing the localization of the sensor inside the needle, along with some markers that we have on the surface of the lung for registering to the anatomy. And then we have the robot being deployed through the bronchoscope. So this is a CT scan render showing the lung anatomy, and we're able to deploy this in a proof of concept of one steer, but achieving similar accuracy to what we had in gelatin. And so this is exciting because what we're showing is that we can train gelatin, and this extrapolates to some other tissues. But there's future research directions, namely in how to parameterize the sampling of the training data set. There's further work to be done there, especially as the workspace of the needle increases. We bounded the workspace to a 75 millimeter insertion length. Extending the estimation to full 3D orientation estimation. Here we're only predicting the orientation component, that's the roll angle, but there's other projected sensing modalities such as ultrasound and fluoroscope that do not provide you any orientation information, but are sensors that are very prevalent in the hospital that would make accessibility to this kind of technology much more accessible. Quantifying the uncertainty of the estimate. This is some work that I've been pursuing. There's a couple of ways to go about that, either with still purely data-driven approaches such as leveraging dropout at runtime, ensemble networking, or hybrid methods. And then extending this to other tissues such as liver and kidneys, which has been done with other steerable needles or other groups working on this. Improving segmentation and registration methods, I'm kind of glossing over that, but lungs are squishy, and when you have a very obstacle-dense environment, it's very hard to register them accurately. And lastly, planning trajectories. These were point targets, but especially when you get into these obstacle-dense environments, having optimal trajectories that avoid all the obstacles and get you there safely is very important. With that, thanks for listening. Some of the people in my group, and I'm happy to take any of your questions.
Yes.
Thank you for the excellent presentation. I just had one question. So in your work, you used a recurrent neural network. Is there any advantage of using this architecture rather than using a convolutional neural network or any other type of architecture?
Yeah, thanks. That's a good question. So yeah, I chose to use a recurrent neural network architecture. It was that long short-term memory network. There's several different types of recurrent neural networks out there that have been shown to work well on time series. More recently, there's been these temporal convolutional neural networks that have come out, and so there's some promise in using those kinds of architectures. Moreover, with the projected sensing modalities that I was talking about, like ultrasound and fluoroscopy, those are acting on image data. And so probably combining it with a convolutional neural network makes a lot of sense.
With regard to those other sensing modalities you mentioned, I know the space for sensors embedded in the needle is incredibly small, but have you done any looking into if there exists an IMU in the world that you could use for gravity direction finding?
Yeah, that's actually a really cool idea. So yeah, I think I've looked into some other people in my lab are looking into leveraging IMU for state estimation. And I think there's one out there you can buy on DigiKey. It's like a 1 millimeter cubed package. So be kind of a large needle or on par with the 6DOF sensing. But I'm not sure if there's any limitations as to making that technology smaller at the moment.
I mean, you might only need two directions of accelerometer for it too, if you just want to find gravity along one axis.
Very cool ideas.
Such a thing exists.
Yeah, talk later.
So thank you very much for the presentation. So you mentioned as an application, so the use of the needle to look into a lung, for example. And my question is, would there be any issues for training your neural network on a realistic data set, because the performance of your method might also depend on the data. So if you want to deploy it on a real person, at some point, would there be any issues in creating data set that is realistic enough? And I think that maybe you won't just put the needle inside real persons to acquire the data first. So
yeah, I see what you're saying. So we often will, I don't know, in that last experiment that was with ex vivo tissue, and so we try to use animal tissue when we can. So I would say that, yeah, if it showed, in this work, we found that gelatin was good enough to steer the needles accurately in ovine brain and the porcine lung. But yeah, if there's tissues that come up where the network does not extrapolate well to them, right, you would want to collect a data set in that tissue type, and you'd probably defer to either ex vivo or cadaver.
Thank you.
Set up for the final discussion. I'm asking the people in the audience, tomorrow we should have had Antonio Bicchi chairing the first session in the morning, but he had physical problems, so he couldn't fly to Malta this afternoon. So I'm asking for a volunteer to chair the first session in the morning. Ideally, we would like to have some faculty, not because we don't think that PhD students can chair a session, but who is willing to, someone who is not chairing another session already. Yeah, you are already, so a different chair from those who have been already recruited. Anyone? Volunteer. Because we already have Cosimo della Santina, João Borges de Souza, Dinesh Thakur, and Christopher Hackman sharing sessions. So we need one more. Come on, one volunteer.
Are there any more professors? I don't think
Postdocs, at least postdoc. Maybe, how about a postdoc? There must be a postdoc. Not even a faculty.
Okay. Bruno, I think we will put a few names and pick one.
Okay.
So don't worry about that, we will do it.
Okay, so we will have a short final discussion about. Yeah. So we will have this short final discussion. To start, I would like to ask you if we, as roboticists, we should see robotics problem differently as we do previously, to take into account advances in machine learning techniques. You have shown us many different facets of what we can do with machine learning, and can we do more? What do you think about that?
Yeah, I guess I could chime in there. So there's no arguing, I guess, with the performance that we get from machine learning methods. These are like purely data-driven approaches that are kind of not making any of the modeling assumptions that we do when we're deriving models based off of first principles. However, there's challenges that come with that, namely the explainability of the model. You can't really prove things about robustness or uncertainty. So I think that there's a lot of future in hybrid methods, having a component of the network that is data-driven and another that is derived off of first principles that can do more explainability of why the thing is doing what it's doing.
Well, I think it's slightly tough with machine learning because they keep printing out papers, so it's hard to keep track with all the newest things. But yeah, I think a lot of some of the newer machine learning that has very nice open source code is easily adaptable to robotics. I think tasks, and that if we can maybe use it to help develop better simulators of some sort, that could also help guide other advances in robotics control or
The other speakers?
Yeah, I can say something about the simulators. I find that a very good idea, and actually in my work I'm using a simulator to generate these stat images, and then I need some work in adapting or generalizing to the real images or the real data, and I think it's a good approach because you can do so many things easily in simulation. I can generate more data, can do planning, but there are limitations. So we need to figure out how to close the gap between simulator and reality. And when in my paper, I'm training a GAN where I adapt between simulated image and real image. But the question is, how do we do that on other data as well? Like, yeah.
So I think I would also like to chime in. So the machine learning methods are quite data hungry, as previous authors correctly pointed out. So an hybrid approach where we could reduce the amount of data that is needed to train on robots. So control mixed with machine learning approaches, I think they would work really well for robotics, where the hardware is involved.
I have another idea. Yeah, I also like the idea of doing a hybrid approach. And what do I want to say? So also like, I believe that real data is most valuable in training the algorithms, but it's very expensive. In simulation, you can generate a lot of data. It's cheap, but it's not that great. So using like a mixture of simulation and real data, and labeling real data is very expensive. So approaches where we only label the one that are most useful, like active learning, and we had it with Sandeep's presentation, only sending the images that are most likely useful and should be annotated. I think that would get us very far, like a hybrid approach where we only label the most interesting data and useful data.
So to go back to your question about the role of machine learning in robotics and its impact, I think there is clear, a great potential of impact. I think the problem is today we are applying machine learning to problems that we know how to solve. We are not applying machine learning to the hard problems that we don't know how to solve. But basically, when we have models, please use the models. When we're talking about contact, if we are dealing with contact, it's high dynamic event that is going to require a lot of attention in the control with your model-based approach. But when we think about what compliant frame we're going to use, we don't know all the time what compliant frame, what input specifications. So at higher level in the control of robots, we really need a lot of perception, and at those higher level, we need machine learning. And this is where machine learning is not really explored. And I think this is really a waste of your energy to not really address the hard problem that we need. I mean, a robotic system is not one loop. It's a multi-layered loop. We have the controllers, and then we are going to deal with the coordination and different things where the perception is at a very low level and the control is at a very low level. I really like your approach when you do the end effector learning. So you're already robot independent, but we know how to move and control a robot to a goal position. We know how to avoid collision. We know how to avoid maybe the local constraints and all of that. The problem is, what is the task? Who's programming? All these other higher level things that are very, very, very hard to come with. And I think that's where we should explore machine learning.
Yes.
Our issues would be to be able to evaluate the performances of what you do by using machine learning, especially when you deal with critical systems. I mean, where you will have to certify the robustness of your implementation. So this will be a limit. Okay, so thank you again for attending the meeting. Thank you, the speakers. We hope you have got a nice day, nice session, nice day with us. And tomorrow we will at 9. Okay, tomorrow at 9, precisely here.